The ellipse kisses that theoretical line for an Earth composition. So it's consistent with an Earth composition, and the higher density is just due to additional compression because you have such a larger amount of mass there. However, the ellipse does seem to lie a little bit below. The center of the ellipse lies below that line, which suggests that it might be a planet more like Mercury. Mercury in our solar system is a little bit overdense for that compared to that Earth composition line. And the current thought is that that's due to collisions that happened early in the history of the solar system. And this is a planet that's also very close to its stars, so perhaps they underwent the same physical processes. So it does look like it's a little bit overdense, but no. I mean, 8.8, if you just look at the density of solid iron on Earth, at standard pressure, it's about that. It's about like a dumbbell. It has a density of about 9 grams per cubic centimeter, but this average density is simply just because it's highly compressed because of the mass. Yes?
How many stars do you sample with a cadence fast enough to do seismology?
512. Yeah, so most of our brightness measurements are taken, co-added to be once every 30 minutes of 156,000 stars or something. We have a smaller number reserved for higher cadence observations that are taken once per minute. And those are the observations that we did of Kepler-10 that allowed us to see the oscillations. Yes?
What would the next instrument look like if you were to
Oh, I bet people are writing observing proposals already to do what's called transmission spectroscopy of Kepler-10b. And so what you do is you take an observation, you collect the light from the star when the planet is right in front of the star, and you know that light from the star is streaming through the atmosphere. And you compare that, and you take a spectrum, or you measure it at certain colors, and then you do the same thing when this planet is not in front of the star, and you compare the two. There's a planet called Gliese 1214b. They did that for that planet and found evidence of a steamy environment around Kepler 1214b. And I'm sure people are going to do the same thing for Kepler-10. So that's transmission spectroscopy. And that will become more sophisticated over the years. We will have new instruments to do it more carefully. Ultimately, over the next some decades, what we want is to build instruments that can look for biomarkers in these atmospheres, See how much methane is there, compare it to what you'd expect from geological activity versus biological processes, oxygen, ozone, all those kinds of things. It's going to be very exciting. Yes?
There's no idea. Why are we even finding planets that are the size of our Earth?
Oh, that's a good question. So the question was, why does it have to be the size of the Earth? So maybe it could be the right temperature, but bigger, right? So the idea is that if you have something, a rock, that grows to be about twice the size of Earth, that's about 10 times as massive as the Earth for that given composition. At that point, gravity, you get this runaway gravitational process where you start accreting on very efficiently all of the light elements that are present in the solar system, like these hydrogen-rich molecules, and that causes the growth of a giant planet. So the current theoretical paradigm is that when you grow a rock to that size, you quickly create a giant planet, depending on where that planet forms. That's all. I mean, if you have something that's very massive also, and it's out at the habitable zone, it's going to hold on to a thick atmosphere. So the conditions, pressure, temperatures are going to be quite different.